Today, we will talk about Raman spectroscopy. I'm Nakkyu and my teammate is Siracosit. We're from KAIST. Let's begin. What can see through Raman spectroscopy? We can identify the molecules by the studying of intermolecular and intramolecular bondings. I will give an example of intermolecular and intramolecular bondings. Please see the figure. It is described the intermolecular and intramolecular bonding of water. Intramolecular bonding is a bonding between atoms in the molecule. So, in this figure, the black line is an intramolecular bonding, and we called it as a polar covalent bonding. And the red dashed line represents the intermolecular bonding between molecules. In this figure, intermolecular bonding is a hydrogen bonding. These bondings have a different vibration motions. When the atoms in the molecules are vibrating, they change the potential energy to kinetic energy and also kinetic energy to potential energy as well. And please see the left figure. This figure represents the potential energy change of atom in the diatomic molecule. And this atom is an example from the hydrogen chloride. The small red circle is the hydrogen, and big green circle is the chloride. And the x-axis represents the length between atom to the other. So it is distance between these two atoms. And y-axis is potential. And as you can see in the figure, the atoms keep vibrating. So kinetic energy and potential energy keep changing. However, the total energy of the kinetic and potential energy, which means the sum of the kinetic energy and potential energy, are constant. So it means that this vibrating mode has a typical energy. So Raman spectroscopy uses this typical energy of vibration mode to distinguish the molecules. When we introduce the light to the sample, the light will scatter out or transmitted. And as you can see in the left figure, the blue dark wave is the incident light, and also it represents the Rayleigh scattering because Rayleigh scattering and the incident light has the same wavelength because the energy is not changed. However, if the scattered light loses some energy, then it is called the Stokes scattering, and the wavelength is changed, and also the frequency is also changed. And as you can see in this figure, the light blue wave. And as I told you, Stokes scattering it changed the wavelength, and so wavelengths increase. So and the frequency is decreased, as you can see in the right figure. And if the scattered light gains some energy from the molecule, then it is called anti-Stokes scattering, and the wavelength should be reduced because it gains some energy, and the frequency will be increased in the right figure. So this shifted frequency or the wavelength represent the typical vibration mode of molecules. Let's look at the example. Left figure is the vibration mode of water molecule, and which are bending and stretching. And this vibration mode absorbs typical amount of energy from the incident light and it will be excited. So the scattered light will have a shifted wavelength from the incident light. And the shifted wavelength of the light is measured and counted as in the right figure. The bending vibration of water molecules shows the 1637 wavelength peak, and the stretching vibration shows the 3450 wavelength peak, roughly. From the previous slide, we saw the principle of Raman spectroscopy. But there is another important principle in Raman spectroscopy. It's called the population of vibration state, because the intensity of shifted peaks are affected by the Boltzmann distribution. At the arbitrary temperature, the population of vibration state follow the Boltzmann distribution. Look at this figure. This figure represents the Boltzmann distributions. The x-axis is the energy of the vibration state, and the y-axis is the population of typical state. And as you can see in the figure, if the energy of vibration state is increasing, then the population is exponentially decreased. So in higher energy vibration state has lower chance to interact with light. Again, left figure is Boltzmann distribution, so please see the right figure. Previously, we said the higher energy vibration state has a lower chance to interact with the light because of the lower populations. So it is connected to the intensity of the Raman peak. The right figure shows the Stokes and the anti-Stokes Raman scattering peaks, and the middle peak is Rayleigh scattering. As you can see in the figure, intensity of Stokes scattering is much higher than anti-Stokes scattering. And this is due to the Boltzmann distribution, because Stokes scattering can be occur in ground state, which means a higher population of molecules. However, anti-Stokes scattering is an excited state of vibration mode, which is occurred in lower population of molecules. Hence, follow the population of state from the Boltzmann distribution, the anti-Stokes show lower intensity than Stokes scattering.
So next we come to the component parts of the Raman spectrometers, which are based on one of the two technologies. We have dispersive Raman and the Fourier transform Raman. Both technologies have four well-known components. The first one we start with the light source, the samples, the filtering equipment, and the detector. However, for the Fourier transform Raman, we have the interferometer as an add-on, and the dispersive Raman, we have the diffraction grating. So the light source right now, we are focusing more on the lasers, which are now used because of the very high power density and the very good monochromatiicities. And for the Raman concept that we have looked, we know that the Raman concept are mostly focused on the changes of the polarizability of the molecules and also the electromagnetism state of an oscillating dipoles. So we can find the relationship between the intensity of the light that emits out and the frequency that the laser shines in from the right equation above. We can see that if the frequency of the light increases, or we can say that the lower the wavelength laser is, the intensity tends to be higher. So in this dispersive Raman, we use a very low wavelength laser, such as the argon laser, which the wavelength is actually around 514 nanometers. But in the Fourier transform Raman, we use a very high wavelength laser, which is around in a yield of 1064 nanometers. So in the comparison, we can see that the peak intensity of the dispersive Raman would be more greater than the peak of the Fourier transform Raman, and the risk of damaging samples of the dispersive would be a bit less than the Fourier transform Raman, because in order to use a high wavelength laser, you have to use a very high intensity. So this lies the question that why Fourier transform Raman spectrometry need to use a very high wavelength of the lasers, because in order to reduce the fluorescence in the samples. So the fluorescence actually caused by the absorption of the incident light, where the frequency does correspond to the electronic excitation states in the molecules. So this absorption actually can cause a heat to the sample, which may destroy the samples. And also the signal that we get from the fluorescent will block the main signal from the strobe Raman, and we cannot analyze anything from the results. So in order to prevent the fluorescence, the first one is we can switch the laser wavelength in order to mismatch the electronic excitation in the molecules. And the second one is we can use a boxcar integrator, which can provide a time gap between the time that the fluorescence will happen and the main time of the strobe Raman will happen. The third one is to defocus the laser light in order to reduce the heat that will cause into the sample. And the fourth one is to minimize the heat by rotating the sample holder. So the concept of the sample actually is the same as the RBS technique, that in each of the angle, the scattering angle, provide the lights differently. So the probability of the scattering of the Rayleigh angle and the Raman angle are different, depends on these two equations. And from the equation here, we can see that the 180-degree back scattering give a very high intensity of the light, more than the 90-degree scattering. But this can be used in both solid, liquid, and gas. However, in solid, there will be one more additional, that the system with a specific defined orientation also can have a very big factor on the proper scattering angles. So next come to the filtering equipment, which the purpose actually is to remove a Rayleigh signal that we didn't use for analyzing out. And there are actually two main classes for the filter in the Raman spectroscopy. The first one is the optical filter. So we have two types of the optical filters. The first one is the LWPH filters, and the second one is the dot filters. And the second one is the tunable filtering spectrometers, which we use the monochromator in order to filter some of the Rayleigh signal counts. So next is the tool that we use in catalyzing frequencies of the scattering lights. So the first one, we use simple microscope interferometers. So they change the signal of the light into the interferogram and proceed to the spectrometer via the Fourier transform. So the advantages of these tools is actually, the first one is they boost the high signal to noise ratio because they do not require any slit to achieve a resolution. And the second one is because the wavelength scales can be calibrated really precise, so it results a very precise wavelength after the analysis. The next one is the diffraction grating, which we use in the dispersion Raman. So they are determined by the two factors in the grating, which is the first is the groove frequency and the blaze angle. So the groove frequency is determined by the wavelength coverage of the frequency that they receive. So if the groove frequency increases, the coverage length of the wavelength will be reduced. And the second one is the blaze angle, which each angle can provide different diffraction intensity. So this is a charge coupled device, which is the detector in the dispersive Raman spectrometry. So in the charge coupled device, we call it the CCD, the element light will shine into the plate, and the plate will build up the charge. So this charge will be read, depends on the frequency, and we can produce the intensity of the peak based on the bright of the light and also the interaction time of the light. So there are 5 factors that also affect to the CCD detectors. The first one is the noise, comes up with the speeds, and also the quantum efficiency, the Italian in IR range, which actually this one is the determiners that tell that we cannot use CCD in the Fourier transform Raman spectroscopy. And the final is the linearity of the CCD detectors. So next is the detector of the Fourier transform Raman spectroscopy. So we can see that after we cannot use the CCD anymore, so however, there are many types of detectors that we can still use. Depends on the wavelength of the lasers that we shine to the samples. So we can see here that there are several detectors that can match to the wavelength that we are looking for. And most of the detectors here actually operates in a low temperature. So what do we get from the Raman spectroscopy? So the characteristic of the Raman frequency actually can tell the composition of material, that what that material is composed of. Does it is an inorganic or is it an organic material? We can tell from this. The second one is the changes in the frequency of the Raman peak, which can tell the stress strain state of that object, because the stress strain state actually affects the vibration of the molecule that cause the shift in the frequency of the Raman peak. The third one is the polarization of the Raman peak can determine the crystal symmetry and the orientation of the molecules. That does that molecules form in a cubic form or in a tetrahedral form, the polarization can tell. The fourth is the width of the Raman peak can determine the quality of the crystal uniformity. So if the structure is very ideal, the width of the Raman peak is very small. And the last is the intensity of the Raman peak can determine the amount of the materials in that composition.
So, simple conclusion of Raman spectroscopy. Raman spectroscopy has pros and cons like the other instrument. So first, about advantages. Raman spectroscopy can use any types of the sample. It means you can prepare into the gas phase or solid phase or even liquid phase. And also, it is good choice for aqueous-based sample like inorganic sample. And it is the kind of non-destructive technique, so it will not destroy your samples. But it also has some disadvantages, like it costs really high compared to other instrumentation. And also it has an interference of fluorescence. And if you choose a very strong laser, it can be damaged to some of your samples as well.